Hello everyone, welcoming you all for the presentation of Material of Engineering. Today I am going to cover third session of the first unit in Basics of Engineering Material. Myself Sumita, lecturer in Mechanical Department, Government Polytechnic, Joida. In the previous session, you have learnt about structure of metals, crystal lattice, characteristics of space lattice and unit cell. Just go through it. Crystal lattice is a symmetrical three-dimensional structural arrangement of atoms, and in this each atom is represented by a single point, and unit cell is the smallest portion of the crystal lattice and it's a simple repeating unit in a crystal structure. In one simple example I can tell, if you consider one wall which is built with the help of the number of bricks, the complete wall can be treated as a crystal lattice, and one bricks which are arranged in a pattern to build a wall, that one brick can be treated as a unit cell. Next move to this session's contents, that is crystal structure, body centered cubic structure, face centered cubic structure, hexagonal close packed structure. We will study in detail about this. Crystal structure. What is crystal structure? Crystal structure is obtained by attaching the atom or group of atoms, and in the crystal cell can be considered as a unit cell is the building block of the crystal structure, and in the common most of the metals possess the cubic or hexagonal structures. It means that in the crystal structure unit cell has the shape of cubic or hexagonal shape. Okay, we will study in details about this crystal structure, how the unit cells and structures are arranged. There are three types of metallic structure, that is body centered cubic structure, face centered cubic structure, hexagonal close packed structure. In short form we can call it as BCC, FCC and HCP. We will study in detail about BCC, FCC and HCP. First one, body centered cubic structure, that is BCC. As I told in previous, the most of the metals have the shape of unit cell shape of the cubes or hexagonal shape. See, in this BCC structure unit cell will be in the shape of cube. See, this is the cube structure, and here the atoms are, how the atoms are arranged. See, one atom at each of its 8 corners. See, this cube has a 8 corners, the one atom present at the each corner and another atom at the body center, and here the body center alli one atom present irutte, and ಅದೇ ತರ 8 ಕಾರ್ನರ್ಸ್ ಕ್ಯೂಬ್ಸ್ ಅಲ್ಲಿ ಏನು 8 ಕಾರ್ನರ್ಸ್ ಇರುತ್ತೆ, ಆ 8 ಕಾರ್ನರ್ಸ್ ಅಲ್ಲೂ ಕೂಡ ಒಂದೊಂದು ಆಟಮ್ಸ್ ಪ್ರೆಸೆಂಟ್ ಇರುತ್ತೆ. ದಿಸ್ ಈಸ್ ಅ BCC structure, and in the BCC structure unit cell shares 8 atoms with the neighboring unit cell. It means that the corners ಅಲ್ಲಿ ಏನು 8 atoms present ಇರುತ್ತೆ ಅದು ನೇಬರ್ ಯೂನಿಟ್ ಸೆಲ್ ಜೊತೆಗೆ ಶೇರ್ ಆಗುತ್ತೆ, not the this body in centered body centered in one atom present ಇರುತ್ತಲ್ಲ ಅದು ನೇಬರ್ ಯೂನಿಟ್ ಸೆಲ್ ಜೊತೆ ಶೇರ್ ಆಗಲ್ಲ. ಸೊ ಕಾರ್ನರ್ಸ್ ಅಲ್ಲಿರೋ ಈ this 8 atoms will the share with the neighboring unit cell. And some example of this BCC structure andre alpha iron and the delta iron. What is this alpha iron and delta iron? That iron from the atmospheric temperature ಇಂದ up to 910 degrees Celsius ವರೆಗೂ ಟೆಂಪರೇಚರ್ ನ ನಾವು ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದ್ರೆ in between this temperature that iron state has called as alpha iron state. In this state the metal structure will be in the form of BCC. And in the delta iron also, the temperature range will be in the 1400 degrees Celsius to 1839 degrees Celsius. In this state, that it is called the delta iron. This delta iron also have the BCC structure. And some common example for the BCC structure are the tungsten, which are used in a bulb, lithium, chromium, sodium, potassium, barium, vanadium, molybdenum, etc. These are some common example. So, BCC, it has 8 atoms at the corner and 1 atom at the center. Next, FCC, that is face centered cubic structure. In this type of structure, this is also has the unit cell has a cube structure. In this, how the atoms are arranged? It contains 1 atom at each side of the corner. Andre likewise in BCC alli yav tara corners alli atoms arrange agirutte, ade tara FCC allu kuda corner alli ondondu atom arrange agirutte. And one more thing, and here ee cubes alli 6 face irutte, aa 6 face center alli ondondu atom present irutte, andre total 14. So, 8 at the corner and 6 at the face. See, it means that 8 corners and the each atom at the its face, and it does not have the body centered unit cell like BCC. BCC tara illi center alli atoms iralla, face alli ashte atoms present irutte. And in BCC, in FCC, the totally 14 atoms are sharing with the neighbor unit cell. How the 14 antandre, see, 8 corners atoms plus 6 face atoms. 8 plus 6 will be 14. 14 atoms will be shared with the neighboring unit cell. Some common example for the FCC is gamma iron. So, as I told in BCC, there will be the iron, there will be the alpha state, gamma state and the delta state. Alpha and delta will be in the BCC structure, and this gamma state, gamma iron state, that is the temperature range is 910 degrees Celsius in the 1400 degrees Celsius. In between, in this range, the gamma iron has the FCC structure. And some common examples andre copper, silver, gold, aluminium, nickel, lead and the platinum. These are the some common example for the FCC. So, hexagonal close packed structure, that is HCP. See here, the unit cell has the shape of the hexagon. In BCC and FCC, unit cell has the shape of cube. So, in this the unit cell has the shape of hexagon. How the atoms are arranged? Each corners of the hexagon prism, 1 atom at the hexagonal face. Andre each corner, ee hexagon prism face alli ಒಂದೊಂದು atom present ಇರುತ್ತೆ and center ಅಲ್ಲಿ 1. ಅಂದರೆ total ಎಷ್ಟು corners 1, 2, 3, 4, 5, 6. 6 corners plus 1 center. Total 7. Likewise in bottom side also 6 atoms plus 7. And also it has the 3 more atoms within the body of the cell. ಅಂದರೆ ಈ prism body ಒಳಗಡೆಗೆ, ಈ hexagonal body ಒಳಗಡೆಗೆ 3 atoms ಮತ್ತೆ ಇರುತ್ತೆ. Total it will share 14 atoms with the neighboring unit cell. How that 14 atoms? See this 6 corners atoms, 6, 1, 2, 3, 4, 5, 6 plus 1 center alli ಒಂದು atom ಇರುತ್ತಲ್ಲ, total 6 plus 1 7. In bottom also 6 plus 1 7, E7 ಮತ್ತೆ E7, 14 atoms with the neighboring unit cell. And some common example for the HCP is magnesium, zinc, titanium, zirconium, beryllium and the cadmium. These are the some common example for the HCP. We will see some related video in this, also some videos. I will show another one video.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next two examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
These are the two video links which I have added here. And next move to the next one is multiple choice question. I'll ask some questions and have give some options. First question is, lead is a metallic crystals having dash structures. Options are FCC, BCC, HCP and none of the above. And the answer is FCC, because in the lead the crystal having the FCC structures. The second question, which of the following has the HCP crystal structure? ಅಂದರೆ ಈ ಕೆಳಗಡೆ ಕೊಟ್ಟಿರೋ ಎಕ್ಸಾಂಪಲ್ಸ್ ಅಲ್ಲಿ ಯಾವುದು HCP crystal structure ಆಗಿರುತ್ತೆ. So first one is lithium, sodium, barium and the zirconium. And the answer is zirconium, because this lithium, sodium, barium has the BCC crystal structure, and only this zirconium has the HCP crystal structure. And the third question is, the structure of the unit cell which is in the shape of hexagon. Unit cell shape hexagonal idre adanna ನಾವು ಏನಂತ ಕರಿತೀವಿ ಅಂತ. So options are BCC, FCC, HCP and none of the above. And the answer is HCP because BCC ಮತ್ತು FCC ಏನಿದೆ unit cell will be in the shape of cube. And the fourth question is, in FCC, the unit cell shares dash atoms with the neighboring unit cell. Your options are 8, 14, 12 and all the above. And the answer is 14 because in FCC, unit cell shares 8 corners atoms plus 6 face atoms. 8 plus 6, that is 14 atoms which will be shared with the neighboring unit cell. Next question is, BCC type of unit cell is found in the metals like. ಅಂದರೆ BCC ಯಾವ ಟೈಪ್ ಮೆಟಲ್ಸ್ ಅಲ್ಲಿ ಇರುತ್ತೆ ಅಂತ. ಆಲ್ಫಾ ಐರನ್, ಗಾಮಾ ಐರನ್, ಡೆಲ್ಟಾ ಐರನ್ and all the mentioned. And the answer is alpha iron and delta iron, that is A and C. In both alpha iron and the delta iron has a BCC structure and this gamma iron has the FCC type of structure. So answer is A and C. Okay. Okay. In this session we have studied about crystal structure, body centered cubic structure, face centered cubic structure, hexagonal closed packed structure. Body BCC has the unit cell has the cube shape and it has a 8 corners plus 1 atom at the body center. And in FCC it is also has the unit cell cube structure and it has the atoms 8 corners atoms and 6 face atoms at the center and hexagonally. So total 6 sides, 6 prism sides ಅಲ್ಲಿ 6 and the center ಅಲ್ಲಿ 1 and top 1 and ಕೆಳಗಡೆ ಕೂಡ 7 and in center body center ಅಲ್ಲಿ 3 more atoms has been shared. These are all the things we have studied in this session and in the next session we will study about microstructure and the types of microscope. Thank you.